This video is to present our tool, DMMPP, to construct dummy main methods for Android applications with path-sensitive predicates. The tool is publicly available at GitHub. We are from Institute of Software, Chinese Academy of Sciences. Android is based on an event-driven model. The Android application lacks of the main method, which is driven by the lifecycle methods and listeners from user interaction. This figure shows the life cycle of an activity, with its lifecycle methods, such as onCreate, onResume, onPause and so on. FlowDroid, a flow-sensitive analysis framework, constructs a dummy main method statically emulating the lifecycle methods as its entry point, which also have been widely reused by other Android analyzers as their entry points. The right figure shows the control flow graph of the dummy main method of activity, according to its life cycle. FlowDroid takes a predicate pi to consider both branches for conditions. Since FlowDroid uses the IFDS algorithm, which is a path-insensitive analysis, the dummy main generated by FlowDroid does not consider whether the path condition is satisfied. However, for path-sensitive analysis, it can affect the analysis accuracy, resulting in false positives and false negatives. For example, predicates generated by FlowDroid for a dummy main method are P1, P2, and P3, whose satisfiability depends on the same variable I, which is path-insensitive. When a path condition in the method is P1, P2, and P3, it is obviously unsatisfiable, causing the lifecycle method unreachability. But a lifecycle method must be reachable as declared by Android platform. The goal of this paper is to construct the crystal predicates for the dummy main method to refine the path-insensitive ones introduced by FlowDroid for the path-sensitive analyzers. We use the Boolean variables from parameters representing the predicates. The path-sensitive predicates will navigate the path exploration in the lifecycle of a component to benefit static analysis. This is the architecture of DMMPP. It is built on the top of FlowDroid and its intermediate representation, IR, a GIMPL, and requires an APK and the lifecycle specifications of components as inputs. It models the lifecycle of components with a unified lifecycle graph. For each component, DMMPP complements its non-explicitly inherited lifecycle method to explicitly indicate component state and constructs the dummy main method with path-sensitive predicates after the complement, according to its lifecycle graph, the syntax and the generation algorithm. A path-sensitive analyzer can use the dummy main method generated by DMMPP directly or use the APK after the persistence indirectly. For the convenience of expression, we formalize a component lifecycle graph with corresponding methods and use it as input to generate dummy the main method. With the CLG, the lifecycle of each component, such as activity, service, broadcast receiver, content provider, and even fragment, can be expressed uniformly. Since the lifecycle method of a component are closely related to its state, and some bug detection depends on its state, if a lifecycle method is not explicitly inherited, DMMPP will complement the method with the parent method invocation. This is the syntax and the algorithm for the dummy main method construction. DMMPP can be used as an API library intrusively, which will be a precursor of an Android static analyzer based on Suite or FlowDroid. It can also be used as an independent, command line tool non-intrusively to generate the dummy main method with the path-sensitive predicate and output the APK with the dummy main method, which can be used for other Android static analyzers or may be converted to be a JAR file as an input of a Java static analyzer. To evaluate the effectiveness of DMMPP, we randomly collect 20 real-world apps, where 10 from FDroid and the other 10 from Google Play, which is also publicly available at GitHub. We choose Androlic to observe the benefits brought by DMMPP, since its approach is path-sensitive. The table shows the number of components, the number of feasible paths, and the construction time overhead for dummy main methods for each APK. The symbol delta represents the increase in the number of feasible paths brought by DMMPP. It can be seen that DMMPP benefits the path-sensitive analyzer with about 43 times more feasible paths than FlowDroid from the dummy main method, with a time overhead of only 41 seconds totally. For each component, the construction time of FlowDroid for the dummy main method is about 16 milliseconds, and DMMPP contributes an additional 172 feasible paths with a time consumption 0.3 seconds on average. DMMPP takes more time because it complements lifecycle methods and constructs a more complete dummy main method. In addition to the insensitive paths mentioned in the motivation example before, FlowDroid contributes so few feasible paths in its dummy main method because it declares that we may skip the complete component. It works for the path-insensitive analysis but breaks down for the path-sensitive analysis. In conclusion, we have introduced DMMPP, which constructs the dummy main method with path-sensitive predicates for Android application analysis. It provides multiple ways for analyzers to use it via the API invocation or the command line. The evaluation demonstrates that it can benefit the path-sensitive analyzer via the dummy main method generated by it with the path-sensitive predicates, providing many feasible paths with a very low time overhead as expected. Again, this video is to present our tool, DMMPP, to construct dummy main methods for Android applications with path-sensitive predicates. The tool is publicly available at GitHub. We are from Institute of Software, Chinese Academy of Sciences.